For the next several sections, we are going to explore what the derivative tells us about a function graphically. So if we remember what a derivative is, it is a function that represents slopes of tangent lines to the original function. That's what f prime of x represents. So it's important that I underline these things here. It's important that we remember that it is itself a function, so we can do things with that function, and that that function represents slopes of tangent lines to the original function. So if the slopes of the tangent lines are positive, that's when the function is increasing. And if the slopes of the tangent lines are negative, that's when the original function is decreasing. So positive slopes on the tangent lines mean the function's increasing. Positive slopes for the tangent line mean the derivative is positive. So when the derivative is positive, the function is increasing, and vice versa. If the function's increasing, then the derivative is positive. And a function is decreasing when the slopes are negative, when the derivative is less than 0 or the slopes are negative. So just kind of pulling together what we know about it and now looking at it like at a big picture, right? When we look at a curve, and I drew tangent lines all over the curve that's already on the screen here, but when we look at a curve, if we can determine where the derivative is positive and where the derivative is negative, as well as these points we've already been looking at, these horizontal tangent lines, it can give us a really good idea of the shape of the curve, the shape of the graph. It can tell us, where we're going up across the page when we hit a horizontal tangent line or maybe a derivative that's undefined, and where we're going down across the page when we're decreasing, the function's decreasing. And so out of this result we get, or out of this, it's not really a result, out of this information, kind of pulling all this information together, we get a test called the increasing decreasing test that just says if we have a function on an interval that's defined and differentiable, so we can also take its derivative, then if the derivative is greater than 0, the function must be increasing on that interval. And if the derivative is less than 0, if the derivative is negative, then the function must be decreasing on that interval. Okay, so that's what we're going to do. We're going to take functions and we're going to take a look at what's happening with their derivatives and figure out from their derivatives where the function is going to be increasing and decreasing. Not only can't we do that, but once we know where it's increasing and decreasing, then we can actually also determine, if we know where it increases and decreases, that will actually give us information about the maxes and the mins. So notice what's happening here. If we know that the function is increasing and then it hits a horizontal tangent line and then starts to decrease, that would automatically have to be a max. And if the opposite order happened, if we knew that a function was decreasing until it got to B, and then at B it had a horizontal tangent line, and then it started to increase, we would know that that's a min. And similar at C, if it was increasing, hit a horizontal tangent line, and then started to decrease, we would automatically know that that must be a max. And you can kind of just think of that in your head, right? If you're increasing, hitting a horizontal tangent line, and decreasing, that has to create a max. And if you decrease and then hit a horizontal tangent line and start to increase, you must be a min. So you've got your maxes and you've got your mins out of just knowing where the function increases, decreases, and where it has horizontal tangent lines or where it has critical points and what's happening at those critical points. Because we could have horizontal tangent lines or we could have corners or cusps that could give us local maxes and mins. Okay, so let's take that information and let's first look at it graphically, and then I want to take what we know graphically and I want to pull it into looking at the function in an algebraic definition. So here we have a curve, let's call it y equals f of x, and let's just say we wanted to know where are the intervals of increase and decrease. So let's list out and talk about how we have to write these intervals. So intervals of increase. Well, where is this function increasing? Well, it's got a couple of key points, I notice, at 1, at 3, and at 5. At all of those points, notice that we have horizontal tangent lines. So we have horizontal tangent lines, and a horizontal tangent line means that f prime of x equals 0, by the way. Notice that we have horizontal tangent lines when x equals 1, 3, and 5. So those are interesting points on the graph. Those are points where things could change, or there's an instant where the slope is 0. And so that is a point where we want to consider what might happen on either side of that particular point. So interesting points, we call them the critical points of this curve, where the derivative is equal to 0. This particular curve, I will put this in parentheses, this particular curve did not have f prime of x is not undefined. It didn't have any places where we had like corners or cusps, but those are also places that we would need to consider if they occurred on the graph. So f prime of x is not undefined for any x on the interval. I'm going to say I for the interval. So we didn't have those, but worth mentioning that we should consider those if they were. Those would also be interesting points on the graph. So what are the intervals of increase? Well, we increase, this curve is increasing from 0 to 1. Okay. Notice I cannot include 1 or 0. 0 is the start. So right, we're not really sure what's happening right at 0. So it's the start of the interval. So it's an open interval. And then 1, we cannot include 1 because 1, f prime of 1 is actually 0. Okay, so it is neither increasing or decreasing at that point. At that critical point, it has that instantaneous rate of change of 0, and 0 is unsigned. It is neither positive nor negative. It's not increasing or decreasing right there. It is simply 0. It has a horizontal tangent line right there, and we cannot include it in the interval. So it's definitely an open interval. And then the next open interval where we're increasing is from 3 to 5. And in a similar way, we cannot include 3 and 5 because we're not actually increasing at 3 or at 5. At those places, the curve has that instant boom where we hit 0 for a derivative. Okay? And it's not increasing or decreasing. For a second, it's not increasing or decreasing. It just has a slope of 0. Then we're increasing again because after 5 we don't start to decrease, right? We didn't, if the slope went negative, we'd be going down. We're actually continuing to increase. So from 5 to 7 we're increasing. So those are the intervals of increase. And then the intervals, actually there's only one, of decrease. So where is the interval of decrease? Well, the interval of decrease here is from 1 to 3. So we have an interval of decrease from 1 to 3. From this, we could also talk about, I didn't write it in the instructions, but we might as well also talk about the local maxes and the local mins. And there's actually only one of each. So the local max, there's a local max at 1, 3. Right here, this point right here, which is 1, 3, is a max. So 1, 3 is a max. If we just say max, we do know that it is local. If we want to classify between absolute and local, we'll always put the absolute on. So just a little subtlety in the notation and the language around maxes and mins. If you have just the word max, it does mean it's a local max. So I wrote max on the curve right here. It's clear that that is not the absolute max. The absolute max actually is up here. And that goes back a couple sections, talking about the absolute maxes and the absolute mins and how they can occur at the endpoints. We'll cycle back to that again eventually, but for right now, we're just talking local maxes and mins. So local max at 1, 3, and over here at 3, 1, at the ordered pair, this is not an interval, this is the ordered pair, 3, 1, we have a local min. Okay? So the maximum and the minimum, the local max and the local min here are at 1, 3, and then at 3, 1. This, by the way, is neither a max nor a min, right? Because we hit a point, we were increasing, we hit a point where we had a horizontal tangent, but then we just kept increasing. So it's neither max nor min. It's not local max or min on that point. Okay, so if we actually just had the graph of the function, we wouldn't really need the derivative to help us graph the function, right? Like we could use the derivative, I guess, to give us some information, more specific information about the graph. But what if we didn't have the graph and all we had was either this information or its derivative that could give us this information? Then we would actually have to put it together. So I want to just take this real quick and I just want to show what's called a sign chart. So a sign chart And it can be for a derivative. It can be, we use sign charts all the time. But I want to use a sign chart for increase, decrease information from a derivative, f prime of x. So let's just suppose, I'll put the graph up there, let's just suppose all I had was this information that we derived from the graph. I didn't have the graph, all I had was the information. Well, remember we were looking at the graph from 0 to 7, and where were my critical points? And let's suppose I did know that I had critical points at 1, 3, and 5. So 1, 3, and 5. I could label those on a modified coordinate plane, just the x-axis actually. I'm just going to put the x-axis here. And I could put these points here knowing that these were my critical points. So I could use my critical points to label. So I used the critical points right here to label this x-axis. So I took the critical points and I put them on the x-axis. Then what I could do is I could take this information, and if I knew the derivative, if I knew where the derivative intervals of increase, remember, is when the derivative is greater than 0. So if I knew where the derivative was greater than 0, I knew it was positive. That means positive. So it was positive from 0 to 1. It was positive from 3 to 5. It was positive from 5 to 7. And then I knew where the derivative was negative. Well, the derivative is negative only from 1 to 3. So this is where we were increasing, decreasing, increasing, and then increasing. Now I also knew that these were critical points. And since these were critical points, this was where and not only were they critical points, but the derivative was actually equal to 0. So f prime of 1 was equal to 0, which is a horizontal tangent. F prime of 3 was equal to 0. F prime of 5 was equal to 0. If I knew that, and I knew that the function was increasing, hitting a horizontal tangent line, then decreasing, decreasing, hitting a horizontal tangent line, then increasing, increasing, hitting a horizontal tangent line, but then continuing to increase, then I would know that this point is a local max, this point here is a local min, and this point here is neither because we increase and then continue to increase. And notice that I actually just kind of very roughly, I didn't even plot any points or anything because I didn't have a function to plot points. If I had a function, I could actually plug those in to find those exact ordered pairs I've just put dots on. And that's what we'll do once we actually have a function. But notice I got, without even, obviously we had it to begin with, but notice just knowing where the derivative was positive and negative in this little sign chart, I can get a very good rough sketch of the curve. Not only can I get a rough sketch of the curve, but I can identify where the local maxes and the local mins are. And so we can do all of that. The sign chart is going to be extra useful for us on the next few examples. So this little sign chart where we take those critical points and we label where the derivative is positive and negative and use that to determine maxes and mins, increase, decrease, all of that information. It's a nice way to organize our information about a curve that we get from the derivative. Okay, that said, let's go look at what that process is going to be and do another example. Okay, the process that I just went through after we had taken a look at that graph, I wanted to give you a little preview of what is called the first derivative test. So the first derivative test uses the derivative of a function to figure out where that function is increasing and decreasing and where it has relative or local max and min values. And so the process goes like this. The first thing we're going to do is find all of the critical points of a function. So remember, critical points, again, this goes back a couple sections, but critical points are the points, critical points, and we mentioned it a second ago too with the other example, where f prime of x equals 0 or f prime of x is undefined. Okay? So those are the points that we're looking for, a little reminder. We're going to figure out where are all the points. We're going to get a list of all the critical points, figuring out where the derivative is 0 or undefined. So we'll take the derivative and we'll figure out where it has its critical points. Then we're going to use those critical points to create a sign chart. And that's the sign chart I previewed for you just a second ago. So we're going to take those critical points and we're going to use them to create a sign chart. We're going to break up the domain or the interval that we're looking at, and we're going to use the critical points to create intervals that we can then look at. The sign of f prime of x. Then we're going to test this. Then we're going to test f prime of x. We're going to figure out where is it positive, where is it negative. Create a sign chart. Where it's positive, it will be increasing. This is just a sample. Obviously, it doesn't have to switch. We looked at an example right here. We looked at an example where it was positive and positive. It increased and then kept increasing. Okay, so we will use a sign chart, putting our critical points onto that sign chart, and then testing the derivative to figure out where the derivative is positive, where the derivative is negative. Okay. After we have that sign chart, we'll know where all the intervals are. So whatever the question might be that we're looking for, whether it be to use it to give a rough sketch or just to state what the intervals of increase and decrease are, we will have all that information. We'll just pull it from the sign chart. Then we can also pull from the sign chart where we have those local maxes and mins. So those local maxes and mins, if we switch from increasing to decreasing, okay, so if we go up and then come back down, that is going to be a local max. And if we go from decreasing to increasing, that will be a local min. Okay, so we'll be able to pull all of that information right out of our sign chart and use it to answer questions or to actually get a rudimentary graph of our function from the derivative. All right, so let's go ahead and actually do that for a problem. Okay, so here we go. Let's determine the intervals of increase and decrease for this function and its local max and min values. So to do this, the process is going to be to take first the derivative. So let's take f prime of x. And so we get 12x cubed minus 24x squared minus 36x. And then we need to find all the critical points. So now let's find the critical points. And remembering that to find the critical points, we have to consider where the derivative is 0 or where the derivative is undefined. So, by the way, there's not going to be any places here where this polynomial is going to be undefined. So there's going to be no critical points from that second possibility. So, but what we do need to figure out is when 12x cubed minus when f prime of x, 12x cubed minus 24x squared minus 36x is equal to 0. And so looking at this, I notice that we can pull out a 12x. That would give me an x squared minus 2x minus 3. Continuing to factor negative 3 and positive 1. And so then I've got okay, so those are my 3 critical points. So now I'm going to go ahead and make a sign chart. So now I'm going to make a sign chart with my 3 critical points. Oh, by the way, there was no restriction on this domain. We could very well have said, look at it just from, we could have said look at it from 1 to 5 or something. And if there had been a restriction on the domain, then of course we would only be needing to look at the sign chart on that restricted domain. Or if the domain itself had a restriction, then of course we would look at just the domain. But since it didn't, we are going to look at it across the whole domain, which is for a polynomial, all reals, or from negative infinity to infinity. So again, this is, basically it's the rectangular coordinate system, but we're only going to look at the horizontal axis, only look at the x-axis for now to get information about what's happening on the graph or for the function. So we're looking at it from negative infinity to infinity. Let's make sure we put this on in the right order. So -1, don't just go 0, 3, -1. That would be nonsense. We don't want to do that. So we'll go -1, and then we've got 0, and then 3. Kind of space them out. I know it's not exactly to scale, but kind of get the idea. And we are going to look at the sign. So it's a sign chart. What we're looking at is the sign of the derivative. And it's going to tell me if the function itself is increasing or decreasing. So increase, decrease of the function. That's what it's giving me. Okay. The sign of the derivative tells me if the function is increasing or decreasing. Okay, so we have basically 1, 2, 3, 4 different intervals. This is the interval from negative infinity to negative 1. I could write it on there. I'm not actually going to write it on there. I just want to be clear. And then this is the interval from negative 1 to 0 and so forth. So that's what is being represented here. What I'm going to write here are the signs. And because it is super helpful to have this factored form of the derivative, I'm going to use that factored form. And so what I'm going to do is I'm going to pick a little test point. Let's use, so something from negative infinity to negative 1. Let's pick a test point like negative 2. So if negative 2 is my test point, I can plug negative 2 in here, and I see that I would get a negative, into the factored form, I would get a negative, 12 times negative 2. Then I can plug a negative 2 in here. Negative 2 minus 3 is also a negative value. I don't care what the actual value is, only the sign. This is a sign chart, remember. And then I can plug negative 2 in here, and this would be a negative. So I end up with, I need to scooch this down just a little bit. I end up with a negative times a negative times a negative. And that gives me a negative. 3 negatives give me a negative on this interval, which means that I am decreasing. The function is decreasing. If the derivative is negative, then the function must be decreasing. And we just keep going. We keep picking test points. We might pick, for this next interval, maybe something like a negative 0.5. And that would give me, so again, I'm just testing into this factored form, so that would give me a negative times a positive, actually. So that results in a positive value, which means we're increasing on that interval. And we just keep going. So we keep going, we pick something from 0 to 3, like 2, plug that in, you get a positive times a negative times a positive, which is a negative. So we're decreasing, and then pick something like 5, and you got your positive times your positive times your positive, and that is an increase. So we now have everything that we need to in order to determine where this function is increasing or decreasing across this whole domain, actually, and where we have maxes and mins. So remember that these points were points where the derivative was equal to 0. These were our critical points, and more importantly, not just critical points, but f prime of negative 1 was equal to 0. So we know we have a horizontal tangent. F prime of 0 was equal to 0, and f prime of 3 was equal to 0. And so then if we think about what this sort of looks like graphically, we're decreasing till we get to that negative 1 where we have a horizontal tangent. Then we start to increase till we get to another horizontal tangent at 0. Then we start to decrease till we get to another horizontal tangent at 3, and then we start to increase. So now I don't know exactly what's happening on this curve, and we're going to clean it up by actually plugging these values in to figure out what the actual heights, right? Like that might be scooched down or that might be scooched up, but the general shape, we definitely have the general shape of this graph. So we have the general shape of the graph. We know that because this decreases then increases, that this point must be a local min, this point must be a local max, and this must be a local min. Now I'm just writing local min max. I'm just writing min and max, but we know that that's a relative or a local, we're not talking absolute. Okay? And so now we could just summarize, and we could say, once we have all that information, we could summarize it and state exactly what's happening. I sped up the video a little bit here and just did the summary here off to the side. So once we have this sign chart, once we've determined where the derivative is positive and negative and know that the function is then increasing and decreasing on those specific intervals, we can just summarize it. So we know that this function is increasing from -1 to 0, and again from 3 to infinity. It's decreasing from -infinity to -1, and then again from 0 to 3. And because of that, and knowing that we also have those horizontal tangent lines at -1 and at 3, if we decrease and increase, we must be a minimum. And so we have those minimums. And notice that the minimums are occurring at x equals -1. And then to find the ordered pair, just plugging it in. So I plugged it into the function to find that it would be 0, and then we also have a minimum at 3, plugged it into the function to figure out that at 3, the minimum value in that small little interval is at -28. Just plugged that in. So this is the actual value of the function. The 0 and the 128 are the values of the function. And then at 0 we had a max, and the max that it was occurring or achieving was 7. So 0, 7, just plugging 0 back into the original function to get the ordered pair. And so that gives us a summary of what's going on the function. And we have a good general shape. Once we have those ordered pairs, clearly we could do a little bit of work to clean up. This is a very rudimentary graph right here, and in another section or two we're going to get really specific about the graphs. It's pretty clear that that needs to go down, right, to get to that -128, but we can kind of see the general shape of the graph, and then obviously it just has a larger dip than I have graphed here to scale. The shape is correct, but it has a larger dip at that 3 for that local minimum value. All right, so that gives us our start on using derivatives to give us loads of information. And we can even use the second derivative to clean this up even more. And we can come back and talk about this function with the second derivative too.